Welcome to this explainer. I am absolutely thrilled you're tuning in today because, wow, we are going to explore a truly monumental transformation happening in medicine right now. I mean, we're literally standing on the edge of a brand new frontier in human health. It's a space where the deepest, most complex mysteries of our biology are finally being unraveled. And today, we're going to look closely at the data and the exact breakthroughs that are driving this massive shift, step by step. So, I want to kick things off with a pretty provocative question. What is artificial intelligence actually doing for human health? Because let's be honest, there is a whole lot of noise out there right now, and we really need to cut through the hype. Today, we aren't talking about your run-of-the-mill chatbots or AI generating fancy emails. No way. We are talking about revolutionary, life-saving medical tools that are actively rewriting what we thought was biologically possible. Okay, let's dive into this. 200 million. That's a huge number, right? Well, that is the exact number of protein structures that Google DeepMind's AlphaFold system has successfully mapped. By predicting the three-dimensional structure of proteins just from their basic amino acid sequences, this AI system actually solved one of biology's most notoriously difficult 50-year-old problems. It mapped virtually every single known protein on Earth. It's like they solved a giant jigsaw puzzle of life itself. To understand the sheer scale of what this means, we've broken today's explainer down into 5 parts. 1. Decoding biology's biggest secrets. 2. Designing new genetic tools. 3. Ending the diagnostic odyssey. 4. Supercharging medical imaging. And finally, 5. The future of patient care. Let's jump right into Section 1, Decoding Biology's Biggest Secrets, the Foundation of Life. You know, mapping the human genome decades ago, that was really just the beginning of this whole journey. DeepMind's Demis Hassabis and John Jumper were actually awarded the 2024 Nobel Prize in Chemistry for AlphaFold. And the reason this is absolutely a Nobel-worthy breakthrough is that this data, which represents more than all previous human scientific work combined, by the way, was made freely available to researchers worldwide. It literally changes the very foundation of biological science forever. And this brilliantly illustrates how having this unprecedented view of molecular structures is immediately speeding up the hunt for treatments. We're talking about our most complex and devastating diseases here. Researchers are already leveraging this massive 3D map to rapidly accelerate drug discovery for cancer, Alzheimer's disease, and even those really stubborn antibiotic-resistant bacterial infections. Which brings us to Section 2, Designing New Genetic Tools, the Paradigm Shift. Thanks to those foundational discoveries we just talked about, we are now crossing a massive boundary. We're moving away from simply observing biology right into active creation. Take Open CRISPR-1. Unveiled in 2024, this was created by Profluent Bio, using large language models that were trained on billions of protein sequences. And what's absolutely fascinating here is that this novel CRISPR-like enzyme was built entirely from scratch by AI. You won't find it anywhere in nature. It's a completely artificial, fully functional gene editor. I just want to pause for a second to really let this massive paradigm shift sink in. The quote says it all. AI is no longer just analyzing biology. It is now designing new biological tools. This perfectly captures the leap we've just made in human history. We are quite literally designing the tools that edit the code of life itself.
Moving on up to Section 3, Ending the Diagnostic Odyssey, Solving Rare Diseases.
But how do we apply all this directly to the individuals and families who are desperately searching for medical answers? First, we have to address what's called the diagnostic odyssey. This is that grueling, years-long search that families endure when they're attempting to find a diagnosis for a rare genetic disease. And it takes such a heavy human toll, draining families emotionally, financially, and usually involving endless tests and heartbreaking misdiagnoses before a breakthrough finally happens. Now, what's really interesting about this slide is the stark contrast in diagnostic accuracy when we actually implement these genomic tools. At Baylor College of Medicine, they integrated an AI genomic search engine to help identify disease-causing gene variants. Traditional methods, they yield about 30% accuracy, but the AI search engine operates at over 85% accuracy. Baylor has literally more than doubled our diagnostic capabilities, which honestly could globally transform how we identify rare diseases. And Baylor isn't alone in this. Harvard Medical School and the Center for Genomic Regulation introduced a system called PopEve. Tools like PopEve are stepping in to identify rare genetic mutations with just unprecedented accuracy. By pinpointing these mutations so quickly, these AI systems are dramatically shortening that painful diagnostic odyssey we just defined.
It's a total game changer for these families.
Let's zoom out a bit for Section 4, Supercharging Medical Imaging, the Clinical Frontline. Now, we're looking at how this technology operates inside actual hospitals, right? On the front lines. Artificial intelligence is now analyzing X-rays, MRI scans, CT scans, and retinal images. And it is doing so with an accuracy that rivals, and in some cases actually exceeds, highly trained human specialists. It's processing all of these incredibly complex visual platforms flawlessly. And I want to remind you why this really matters to all of us. Because spotting conditions like cancer, diabetic retinopathy, and heart disease earlier than ever before, that is the absolute key to saving lives. Earlier detection directly translates to earlier treatment, and that means dramatically better patient outcomes across the board. Let's move to our final part, Section 5, the future of patient care, data-driven medicine. Let's see how this spills right into the daily workflow of the doctors who are actually treating us. Imagine a physician requires guidance right at the point of care. Traditionally, they'd have to sift through journals for hours. But now, a platform like Open Evidence can synthesize the entire body of current medical literature. The doctor receives evidence-based guidance in seconds. Replacing hours of reading with just seconds of synthesis gives doctors instant access to the absolute latest research, literally while the patient is still sitting right there in the exam room. And when it comes to deciding on a treatment plan, machine learning models now look at all these biological layers simultaneously. They're looking at genomic sequences to spot disease patterns in oncology, analyzing protein expression for molecular signatures to build highly targeted treatments, and tracking cellular behavior to find what human specialists might miss in precision medicine. It's creating these highly targeted treatments that no human could ever calculate manually. So what does this all mean? We've seen how we went from an AI that maps the microscopic foundation of life to building brand new genetic tools from scratch, to doubling diagnostic accuracy, and finally putting this powerful data right into the hands of our doctors. So I'll leave you with this. If AI can map the microscopic foundation of life and design new genetic tools today, what incurable diseases will it help us defeat tomorrow? Thank you so much for exploring this fascinating topic with me. Keep questioning and keep learning.